MATLAB, there's a function called huff peaks, which, by the way, you're not going to be allowed to use because you're going to have to write your own peak finder. All right? Well, anyway, let's assume you found just one d in theta. Well, the line itself would be d is equal to x cosine theta minus y sine theta. Get it? That's all there is to finding these lines given the edge points. So we did an algorithm. Whenever you do an algorithm, you just need to think about things like how well does it work? Well, obviously it works great because I'm telling you about it. No, we'll see that in a minute. More importantly, for algorithms, we have to talk about things like complexity. So the first question is, this is an easy one, what's the space complexity? That is, how much memory do I have to use? Well, forgetting the image for a moment, the bottom line is I need k to the n bins. All right? So if I have k bins in each dimension, it's k to the n is the number of bins. So we were doing this in 2 dimensions, so it would be k squared. So, if I have about 100, so it's about 10,000 maybe. That should tell you, and this is going to come up in our next lesson, that adding the number of parameters, which increases n in this case, can be very expensive in terms of memory. In fact, also in your problem set, you're going to try to do something and you're going to blow up MATLAB, and then you're going to figure out how to fix it. What about time complexity in terms of the voting? Well, the nice thing is that the voting is linearly proportional to the number of edge points. You run through your edge points and they each vote. And the voting might take a little bit of time, but it's constant. All right? Compare that, let's suppose you're trying to fit a circle. Okay? So a circle is defined by 3 points. So if you have some large number of edge points, the number of triples is that number, let's call it q. Q choose 3 would be a very big number. Right? Whereas if you do something that's proportional to just q, you're in much better shape. So the idea here is that the time complexity is constant in the number of features or edge points that you've detected. Let's take a look at some examples, some toy examples and then some real examples. Here we have a cartoon example of an image on the left that just has a bunch of dots in it. And those dots happen to all lie on a line, which is good. So this is a noise-free huff example, of which there are none in the real universe, but I've got one here. No, I was about to say I made one. No, I stole this one. Others I've made, these I stole. So on the left here, in image space, we have a bunch of points that all lie on a line. And they lie on a perfect line, so that's how you know this is a cartoon example, because that never actually happens for real. What we have on the right are the votes. And what you can see here is that each dot is creating a particular trace. And you'll notice that those are parts of sinusoids. Okay, here's another one. And that comes from that equation that I was saying before. And what's most important is all the votes over here line up, and that's how we would know that's where the line is. See? So cool. All right, suppose I showed you the picture of a square, all right, and I ran an edge detector on it. What would you expect to see in huff space? Well, let's see. How many lines do we have on a square? That you learned hopefully before 7th grade. There would be 4 lines. Okay, and you would get a huff accumulator array, a voting thing that looks like this. And here you see that there are 4 peaks. It's a little hard to see sometime in the image, but the idea is that the values there are much higher than the values elsewhere, and you can see how the votes overlap. So here you would know that there were 4 lines, and you'd be able to pull them out. Okay. Here's another Blocks World scene. You can see that there's a bunch of edges there, and here's the huff array. And you can see there's sort of sinusoids dancing all over the place. Here, by the way, you see one really big bright spot. What's that spot going to be? Well, that's going to correspond to this nice, big, long edge. There are other spots, and that makes sense because there are other lines. But this big, bright one is going to be the longest one because it has the most votes. We'll take a minute here to do a little demonstration of using a huff transform that's built into MATLAB. And I'll repeat, on your problem set you're going to be doing some huff code, and you're not to use the huff implementation that's already there, nor anybody else's huff implementation that you have from the web. Because it turns out when you go and write your huff implementation, certain things are going to break, and it's in that experience of it breaking that you're going to learn what the important elements of it are.
To detect lines in an image, we first need to find edge pixels. So let's load an image, convert it to grayscale, and find edge pixels using the canny operator. Let's see what these look like. Here's the original image. As you can see, it has some lines in it, the grayscale version, and edge pixels. Now we'll apply the huff transform method to find lines. For this, we'll use the huff function in MATLAB. Find out more about this function in the MATLAB documentation. The equivalent function in Octave is hufTF. The first return value is the accumulator array. The second is a vector of theta values, or angles. And third is a vector of radius values, or rho. Let's see what this looks like. We pass in the theta and rho values to properly label each axis. Rho, or distance from origin, is along the y-axis, and the angle theta is on the x-axis, ranging from -90 to +90. Okay, so let's find the peaks in this accumulator array. We pass in 100 as the maximum number of peaks we are interested in. Note that a similar function called immaximas needs to be used in Octave. Let's plot these peaks on the huff accumulator array. Note that we need to use the theta and rho values to plot the peaks correctly. The peaks are marked by small red boxes. The size of the peaks matrix is 13 by 2. 13 peaks were found. Each row contains the location of a peak. The first column has rho values or y values, and the second one has x values. Using these peaks, we can find line segments using the huffLines function in MATLAB. It looks like 28 line segments were found. Each element in line segs is a structure with the two endpoints, the theta and the rho values. Let's plot these line segments. As you can see, most of the longer line segments have been detected, but a lot of spurious line segments also show up. Okay, so how can we get better results? Let's take a look at the edge pixels again. We notice that there are breaks along the longer lines in some areas. There is also this dense grouping of curves that could throw the huff detector off. To find a set of cleaner or more meaningful lines, we can do multiple things. For instance, we could increase the threshold parameter for huff peaks. To understand what these parameters mean, let's look at the documentation for this function. So threshold is the minimum value in the accumulator array, that is the minimum number of pixels that support a line required for that line to be counted as a valid candidate. Any possible lines with less pixels will not be considered. Here we set it to be 0.6 times the maximum value in the accumulator array, the default being 0.5 times max. Neighborhood size defines the region over which local maxima will be computed. Note that this is not a region in the image. We are computing local maxima in the accumulator array. So the size of the neighborhood is defined in rho and theta dimensions. A neighborhood size of 5 degrees along the theta dimension means that a strong line will suppress other lines that are similar but slightly off in direction. Recall that we found 13 peaks in our last attempt. This time we have only 7 peaks. Let's see where these peaks are. Looks like we might have cleaner results after all. Let's compare this with the previous accumulator peaks. We see that a lot of the previously found peaks in this dense region are now gone. The new peaks are clustered around 3 major locations. Okay, what more can we do? We could play with the parameters of huffLines. How about we increase the fill gap parameter to 50? This is the maximum number of pixels allowed between two segments for them to be counted as one if they lie along the same line. To focus on longer lines, let's increase the minimum length to be 100 pixels. For a better understanding of these parameters, take a look at the documentation for huffLines. Okay, let's see what the new segments look like. Compared with the previous results, we see that the false positives have been mostly removed. Some of the previously broken segments have also been joined. Obviously, you can do a better job by playing with the parameters, especially here. So feel free to play with the huff transform functions.
Here I'll show you an example of huff running on a real image to show you that what it does well and what it doesn't do well. This is a picture of an American football field. This is American football, played with a ball that's not round. We run an edge detector of some flavor and we get out these edges, and those are some interesting looking edges. And then what we do is we run that through a Huff accumulator array. You can see the sinusoids here, sort of spread out, but you're seeing that these squares are all of these peaks that were found. And this is using some code that tries to look for peaks. And you'll notice that a whole bunch of them are very close together, right? So being very close together would mean that they're about the same angle and that they're approximately in the same location. Same angle, same location. Well, yes. I mean, here are lines that are the same angle and about the same location, and here, and here, and here. And even here, about the same angle, about the same location. So you would expect to find peaks that are nearby. So I'm showing you this peak image here. If I were to draw the lines associated with each one of these peaks, I would see something that looks like this. So there's good news and bad news on here. The good news is that it found an awful lot of line segments, okay? You'll notice it also missed a bunch, okay? Why is that? Well, that has something to do with the nature of the edges that were found and the bins and the voting. These are all details that are going to matter in terms of how well you find the edges. You'll also notice that there is this cyan line here, and that's the longest line segment found. Now, somebody should be saying, wait a minute, line segments? What do you mean by line segments?
Line segments? What do you mean by line segments?
Well, in the Huff transform, when you find a theta and d, or an m and b for that matter, that's an infinite line, right? That's a line that goes as far as you want to. It certainly goes through the entire image. If you want to find the line segments of the points that voted for that line and just connect them, or just connect the two that are farthermost away, or do some other operation of running along that infinite line, seeing if there's an edge point near there or anywhere near there. So you have to do some other operation besides the voting we just showed in order to find the line segments. The good news for you is that in your problem set, I just want you to find the infinite line. You don't have to worry about finding the line segment that's actually supported in the image. A couple little things to look at remaining. The first is the impact of noise on the Huff transform. So here what you can see is an image on the left where we've taken that same cartoon set of dots and we've perturbed them a little bit off the line. So we've added a little bit of noise to their location. On the right, you see the Huff votes. And you'll notice that now the peak, not so precise. And in fact, if we had very, very fine bins, we might miss that peak altogether. So in a minute, we're going to talk a little bit about changing bin sizes with respect to noise as a way of making the thing work. But what happens is that small amounts of noise can bump you off. So by the way, one really kind of cool thing you could do, if you wanted to find sort of the general peak over here, what might you do? You might smooth this image, right? You could actually take say a filtering of that as an image. Then find the peaks. Now you know you've moved the peaks around a little bit because you've blurred it, but now you at least found the peak, and you could say, I'm going to do the Huff transform again, but this time I'm going to just focus on that area. Okay, so I'm going to build a new array with much finer bins, but only there, and if D or theta are outside there, I'm not even going to count those votes, and that would let you go from a noisy image to a better one. There's actually another problem. What happens if we have a lot of noise? Like, suppose all we have is noise. Here on the left, what you've got is a bunch of points that are put down that are just randomly put there. And on the right, everybody gets to vote. Laura Croft or whoever you want, go ahead and vote. Turns out there were no real candidates. But maybe we don't know that. You can accidentally find peaks. So sometimes you have to worry about, is the peak that I'm finding actually real or not? It's helpful if you already know. Let's suppose you know there's 6 lines in the picture. Well, then you just find the 6 highest peaks. But if you don't know how many are there, you have this question of when is a peak a real peak and when is it just the accidental alignment of votes? To conclude this lesson, I want to talk about a couple of extensions to the Huff transform. And then some of these extensions are going to carry over both to the next lesson and the one after. By far, sort of the extension that people leverage the most is the one shown here using the gradient. You'll notice that our algorithm is almost exactly the same. We initialize our accumulator array, we iterate over each point, but now instead of looping or iterating over all possible orientations, we actually take the gradient at that point and we take theta from that gradient. Now, you could take a single theta, or you might even take a range of thetas where you say, well, I know that it's, you know, approximately 45 degrees plus or minus 10, so I'll vote from minus 35 to 55, but I don't